Transparent Physics is very proud to present NoobsterClass, courses for people that don't know much about the topic. Our current Noobster class, adding two-dimensional vectors. Today's lesson, angles exist. Let's start with a Noobster class disclaimer. Your teacher or professor may not cover this content in the exact same way I do in this course, and that's okay. Every approach has its advantages, every approach has its drawbacks. Ultimately, we all end up with the same answer anyway. Find the style that works best for you, stick with it. Unless, of course, your teacher has a specific way they want you to do it, then do it their way. So if we're going to dedicate an entire course to this, we should probably make sure we address what exactly is two-dimensional vector addition. Well, first of all, a reminder that a vector is a measurement that includes a magnitude and a direction. And there are lots of measurements in physics that are vector quantities, displacements, accelerations, forces, just to name a couple to begin with. And so we're going to need to be able to deal with those mathematically as they arise. And being able to add vectors together gives us options in understanding the scenario better. For instance, let's say we have two displacement vectors and you travel for a certain distance and then you turn and travel again for a shorter distance, and you want to tell your friend exactly where you are now. Well, how do you do that? At 13 kilometers and 8 kilometers, what does that mean? Are we 21 kilometers away from where we started? The answer is no. There's a math behind how to solve for that answer as represented by the green vector here, and we're going to talk about how to do that. And that ability to add multiple vectors together has a lot of functionality in many different scenarios in physics. And you might be asking yourself, whoa, did I miss the one-dimensional vector addition video series? And the answer is no, you didn't, because it wouldn't really be very long. It's pretty easy to do. As a reminder, when we're talking about one-dimensional vectors, we can indicate their directions pretty much with just pluses and minuses. And we can then just add them together algebraically. You can use all the techniques that we're going to show with one-dimensional vectors, but it's really overkill. Let me show you what I mean. So one-dimensional vector, let's say left vectors, right vectors. So a vector says, hey, I go to the right 4 meters. That's plus 4 meters. And then I go to the left 2 meters. That's minus 2 meters. One-dimensional vector addition is simply adding those two together. Plus 4 plus a minus 2 is equal to plus 2. So you're 2 meters to the right of where you started. That's it. Another example, you go 2 meters to the right, that's plus 2 meters. Then you go 4 meters to the left, that's minus 4 meters. How far are you from where you started? Positive 2 meters plus a negative 4 meters gets you a negative 2 meters. You are negative 2 meters to the left of where you started. And that's it. You've got one-dimensional vectors down. As a quick overview of where this Noobster class is headed, we are going to be learning how to add vectors that are pointing in any direction together. But in order to do that, we're going to learn and build from a series of simpler steps. Today's lesson deals with angles, specifically defining how we can write angles with regard to what's called a standard angle, which is going to help us unlock some powerful trigonometric abilities later on. The next lesson is going to be involving some perhaps review math with the right triangle, including Pythagorean theorem and SOHCAHTOA. We're going to start putting some of those things together then by developing a resultant vector from two perpendicular vectors. Then we're going to reverse that process and break a resultant vector up into two perpendicular components. And then we have all the pieces we need to analyze any number of vectors acting in any direction with the help of the VAT. And we'll have much more to say about that later in the course. Okay, before we get into the bulk of this lesson today, probably a good time for a tea break. Maybe pause if you don't have one handy and brew yourself a cup of tea right now. Physics is always a little sweeter with a cup of hot tea by your side. And by the time we're wrapped up with this lesson, you will be able to understand quadrant notation. you're going to be able to describe how a standard angle is measured, and you'll have had plenty of practice measuring both positive and negative standard angles. Okay, the teams are ready to take the field, and we should probably get a bit of a lay of the land first. You can see already you've got your X and Y coordinate system. The middle of it is called the origin. And again, the x-axis is the horizontal axis and the y-axis is the vertical axis. And if we start at the origin and work our way outwards, if we go to the right, that is considered to be the positive x-axis, and that points at what's called 0 degrees. If we start at the middle and go up, that is the positive y-axis, and that's 90 degrees. If we start at the middle and go to the left, that is the negative x-axis, also known as 180 degrees. And then if we start at the middle and work our way down, that is the negative y-axis, which is 270 degrees. You can see that each designation is a 90-degree angle. That's a right angle. So 0 to 90, 90 to 180, 180 to 270, and 270 to 0 degrees. Each of these are called quadrants, and the quadrants are designated 1, 2, 3, and 4. And we'll have more to say about the quadrants as we go through this series. But for now, it's just a good thing to know. If somebody says the vector's in quadrant 2, what does that mean? And the term quadrant is based off the Latin word for fourth. So breaking something into fourths is breaking it into quadrants. So the star of the show today is the standard angle. And you can see on our XY coordinate system, I've drawn a vector arrow. And arrows make great representations for vectors because arrows have lengths and arrows have direction and vectors have lengths and direction. So arrows make great vectors. Now the standard angle is measured starting from the positive x-axis. The positive x-axis is the one that goes to the right. And if you were standing on the positive x-axis, you could think of sort of a plus and a minus with respect to you standing there. Plus would be up and minus would be down. So if we go up from the positive x-axis, that would be considered a counterclockwise measurement. The angle would be considered a positive angle. So for example, that would be positive 45 degrees. But that's not the only way that we can measure that angle. We could choose instead to start at the positive x-axis, and instead of going up, we could go down. So our angle would go clockwise around instead of counterclockwise. When we go down, we're hitting negative angles instead of positive angles. So we still have designations for each of the axes, but it's flipped kind of like the upside down from where we would expect to see it for positive angles. So going from 0 down to negative x is negative 90, because that's the first one that we hit on the way around. Then we go to negative 180, then we get to negative 270, and then we complete the circle. So going down puts us in the negative coordinate axis, but it's still the same ultimate angle. It doesn't matter which one you put in. So in this case, if we start at the positive x-axis and go clockwise, we spin all the way around past negative 90, past 180, past negative 270, and we get to 45 degrees past 270, which is going to be negative 315 degrees. Both of these answers are entirely correct. If you plug these into your calculators, they mean the exact same thing. So is one a better answer than the other? Well, I mean, one might be a more convenient one to figure out for certain circumstances, but ultimately it comes down a lot to personal preference. Okay, so now we're going to practice getting both positive and negative standard angles for the same vector. I will note that in an actual physics problem environment, you're not going to be solving for both of these angles. One of them is fine, the positive or the negative, and then you just move on. So first problem, we've got a vector that's a little off from the positive y-axis in quadrant 1. And so we always start at the positive x-axis. We note that the positive angle is going to go up counterclockwise from the positive x-axis. And the 20 degrees that's referenced is with respect to the 90-degree positive y-axis. So we can see that the vector in question comes up 20 degrees short of 90 degrees. So if it's 20 degrees short of 90 degrees, that would mean that it has a positive angle of 70 degrees. Now that is clearly the easier way to go about it, but we don't have to do it that way. If we want to use the negative angle, we would drop down, spin all the way around, and remember that in terms of sort of the upside down, 90 degrees is going to become 270 degrees, negative 270 degrees. So the angle goes around past negative 90, past negative 180, past negative 270, and it goes 20 degrees past negative 270, which is going to make that angle negative 290. They are both equally acceptable answers. Positive 70 degrees is the exact same as negative 290 degrees. And just for giggles, if you take the absolute value of both of those and add them together, you can see you get 360 degrees, which is, of course, the total number of degrees in a circle. Let's take a look at the next one. It is 30 degrees off of the negative x-axis, and it's sort of up in quadrant 2. So just off the bat, if we were going positive angle, we would expect it to be somewhere between 90 and 180. Again, we start at the positive x-axis, always start at the positive x-axis, so we draw it through quadrant 1 into quadrant 2, so we know it's going to be past 90 degrees. If we take a look, the way that 30 degree angle is referenced, we know where 180 degrees is. So we can see that it is 30 degrees short of 180 degrees, so we could list that as positive 150 degrees. If we want to do the negative angle, again, we start at the same place, we end at the same place, but we drop down instead of going up. So we drop past negative 90, we come around, and instead of it being positive 180, it's negative 180 now. And it's 30 degrees past negative 180, which means it's going to be negative 210. Again, equivalent angles, and you can see if we take the absolute values, they again add up to 360. So that's a good check to make sure you're doing it correct. Let's take a look at a couple more. The next one is an example of what it might look like if it's sitting on one of the axes. Again, if you know what you're doing at this point, you can see that since it's sitting on an axis, we do start at the positive x-axis, we spin around. Going around like that is 0, 90, 180, 270. So since it's sitting on 270, it is positive 270 degrees. And if we drop down instead from the positive x-axis into the upside down, into the negative world, that is going to be hitting negative 90 as an axis. So the angle is negative 90. If we take that off just a little bit and we look at a vector that's in quadrant 4, we have positive x-axis identified. Now in this case, the positive angle is probably not the one that you would use. It's a little inconvenient at this point. You spin all the way around through quadrant 1, through quadrant 2, through quadrant 3, into quadrant 4. So we go a smidge past 270. It's 10 degrees past 270. So that's going to be positive 280 degrees. But that's kind of a lot of work. So in this case, the negative angle might actually be a very, very smart choice to use, because you're going to take it, you're going to drop down from the positive x-axis. You can see that you are just shy of being at negative 90 degrees. So the actual answer is negative 80 degrees. And 280 and 80 is 360 once again. So standard angles should not be underestimated. The success in this Noobster course depends on you being able to correctly identify these standard angles. But when you use standard angles, you tap into a lot of tools that are available to you that's ultimately going to make solving these problems much easier, because we're going to rely on very powerful mathematical operations that are unlockable if we use this standard angle notation. So come along for the ride, and let's add some two-dimensional vectors. If you like what you've seen from this Noobster class so far, why not let YouTube know that? If you have any questions about the material, or you have a better way to do something, leave it in the comments. And to be informed when the next transparent physics content is coming out, make sure you subscribe. And as always, thanks for watching, even if your physics teacher is making you do this. I hope I've made standard angles a little clearer for you on this episode of Transparent Physics.